In this lecture, we are going to study about the specific heat of crystal and and some models which we are going to implement while studying the specific heat of a crystal. So, specific heat of a crystal. So, specific heat is considered at a constant volume. So, it is considered at a constant volume. It represents how the derivative of internal energy of the system with respect the temperature at a constant volume, that is Cv is equal to 1 by n dou u by dou t at a given volume. Here 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 n is the number of moles in a crystal. Now let's look at the behavior of specific heat with respect to temperature. So let me plot the graph. So this is y-axis, this is x-axis. On x-axis there is temperature, on y-axis there is specific heat at constant volume, and the graph looks something like in this fashion. So this is 3R here and this is constant here. So if you remember, the behavior is T cube. This is cubic behavior at the beginning, and at very small temperature then it goes to a constant value as seen in the graph. The constant value for 1 mole of a material is 3R. Here R is the gas constant. Here R is the gas constant. If you go for very high temperature, you can see there is a very small increase in Cv at this point. So very small increase in Cv at very high temperature. So, and if you go at very lower temperature, we have a small linear behavior like here. This is a linear behavior here, small linear behavior, and suddenly you can see that the graph becomes T cube, take the forms of T cube. Now you should think that the internal energy arises in this case due to the two possibilities. First one is the due to the moment of electrons, and second possibility is due to the moment of ions. So the electrons contribute only at a small temperature. That is, electrons contribute only at a small temperature. Where the curve is almost linear, like in this region. And all the rest curve, like T cube to constant, the curve is related to the, and all the rest curve let me write full. and rest of the curve and all the rest of curve is related to the contribution of by ionic motion. So we need a good model to understand the ionic motion. The first model, which is generally wrong, like every first assumption, is to find the ionic motion was Dulong-Petit model. So the first model for finding the ionic motion was Dulong-Petit model. Now let's dive into the Dulong-Petit model here. Now we have to take a model of the crystal. We have to take a model of the crystal where we have ions, in this fashion. And we have to consider, and each ion moves around the equilibrium position. So basically, this is the frozen crystal, that is ions in the periodic lattice. Now, if you increase the temperature, the ions can move around equilibrium position with very small movement. So it's like each atom is in the bottom of the potential. Now, so the model is that each ion is attached with a spring, which is not true in real case. But this model considers that each atom is attached to a spring with certain mass m and has spring constant of k. So the model is that each ion is attached with a spring of constant k to the equilibrium position. So when the ion moves, it goes back to the equilibrium position. It is not true that the atoms are attached to a spring, but it is just the representation of the quadratic potential. So what is the 1D harmonic oscillator? What is the energy of 1D harmonic oscillator? So it is a case of 1D harmonic oscillator. So energy of 1D 1D harmonic oscillator, 1D harmonic oscillator is given by E equal to px squared by 2m plus half kx square. So this is the kinetic energy term, and this is the potential energy term. And here we have a potential in this fashion, but if you approximate the bottom of the potential with a parabola in this fashion, it's like having a spring. That is, the effect is the same. So K is not a spring. Actually, K is not a spring. But it is related to the curvature of this potential. So we assume that vibration is small. Of course, atom in a crystal is a 3D oscillator. So what is the average energy of the crystal? So the next question is, what is the average energy of this crystal? In imagine that all the ions here are the ions. We have to imagine all the ions are attached to a spring. Okay. So for simplicity, let's consider a simple crystal. So mass is always the same. The spring is always the same. So the shape of the potential is always the same. So when these atoms are vibrating or moving, the energy will change. If we increase the temperature, we will have more vibrations. So what is the internal energy U of the system? So this is a thermodynamic quantity, that is the average. U is the average energy of the system. So it is equal to the number of atoms multiplied by the average energy of each atom at the temperature T. That is, it is given by this equation. This is the number of atoms, and this is average energy of each atom, average energy of each atom at the temperature T. So the next question is that how much is the average energy of each particle at temperature T? So let's consider a 1D system. For each degree of freedom of the system, we have average energy of half kT. Atom in the gas can move in three directions, so it has 3 degree of freedom. So in 3-dimensional, average energy is 3 by 2 kT. From this equation, that is px square by 2m plus half kx square, we can infer that we have 2 degree of freedom, 1 degree of freedom for kinetic energy and 1 degree of freedom for potential energy. So the average energy in this case is given by kT. So after substituting the value of average energy in the equation, we are going to get U equal to, that is, U is given by number of atoms multiplied by the average energy of each particle. So after the substituting value of kT in this equation, we are going to get n dot kT. This is for 1-dimensional case. For 3-dimensional, we have 3 degree of freedom. So for 3 degree of freedom, the above expression is given by this expression. This model is not completely correct. So anyhow, we are in future lectures, we are going to study more good models in comparison to this Dulong-Petit model, that is the Einstein model and Debye model. But now let's calculate the specific heat. We know that the specific heat is given by Cv is equal to dou U by dou T. Now let's differentiate the above term, that is 3n kT. We are going to get 3 Na k, which is equal to 3r. Here Na is the number of atoms in 1 mole, that is Avogadro number, and K is the Boltzmann constant, and here R is the gas constant. Now let's plot the curve again. This is CV and this is temperature. So the curve looks something like this one. That like is at high temperature, and this is 3R. Okay, so basically Dulong-Petit model explain this constant region. So this region is explained by the Dulong-Petit model. But for Dulong-Petit, we have always the graphical values. So specific heat is a constant which doesn't change with temperature. So there is something right and something wrong with this model. So to understand this calculation, it is enough to believe that for the system equal to px square by 2m plus half kx square, the average thermal energy is half kT. The average thermal energy is half kT for each degree of freedom. So here we have degree of freedom related to the kinetic energy and potential energy in all three directions. Now we want to calculate kT starting from this equation, that is px square by 2m plus half kx square, in another way. We will use some statistical physics. So what is the average value of energy at temperature T? So our goal is to find this. So it is the average value of Hamilton function, that is, it is the average value of Hamilton function. So Dulong-Petit model is completely classical. So we don't have quantum physics here. Some sort of quantum physics we don't have in this model. So this is one of the wrong point in this model. Hamilton function is the energy of system expressed in terms of position and momentum. That is, so for 1D harmonic oscillator, the equation becomes some sort of in this fashion, because Hamilton function is the function of the position and momentum. So how do you calculate the average value of energy in a classical system? So this is your next question. How are you going to calculate the average value of energy in a classical system? So this is the thermodynamics of gas. So what is the statistical function distribution for energy in a classical physics? That is Maxwell-Boltzmann statistics. Maxwell-Boltzmann statistics. So where the probability is proportional to e power minus e by kt. So using the Hamilton function formulation, this average energy, probably believe that if particle can be in different position of the phase space is the combination of the real space and momentum space. So this is the integral in a phase space of the energy multiplied to a probability to have this energy, and integrated for all possible position. Like this is given by this equation. This is the integration over phase space, which is the Hamilton function, which is a function of position and momentum multiplied by the probability to have this energy. That is by kt dx dot dpx. So we have also to normalize, because we have to fix the integral of this probability, that is e power minus e by kt should be equal to 1. So we have to divide by the integral of this probability. So after normalizing, we are going to get some sort of this equation. After normalizing, we are going to get phase space multiplied by the probability of energy, probability of the state having this energy, that is okay by so in the above integral, so in this integral, if we substitute px squared by 2m plus half k squared equal to hx px, then we are going to get kt equal to kt. Now in the next lecture we are going to discuss more improved model, that is Einstein model. So for now, thank you.